Hi, and welcome to lesson 10.3, the independent practice. And first we have uh, Josie recorded the average monthly temperatures for 2 cities in the state where she lives. Use the data for numbers 5 through 7. So 1 month, and this is all in Fahrenheit here. So 1 month it was, average temperature was 23. It must be cold out there. It got as high as 86. Oh, how many are there here? It should be 12 maybe, huh? For two, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So she did a full year then. And okay, so then for city one, what is the mean of the average monthly temperatures? And what's the mean of the absolute deviation of the monthly temperatures? My answers are here. So the mean is 50 and the mad is 13. I'd like to show you how I get that. And for that, I have this right here. We have this. So here are all the data points for the city. What, city one? Yeah, city one. This is all the data for city one, all the monthly temperatures. So you add them all up, and that sum is 600. And you take that 600 divided by 12, and it's 50. Now that 50 gets used in all of the data. It has to be subtracted from each data point. So we have, and you know what? I think I'm going to switch this here. I'm going to make this red. Hopefully this is a little bit easier to see. So here I have 23 subtracted from 50. So, you know, the difference between 23 and 50 is 27. And then 38. 38 is the next one. 38 from 50. See, the 50 repeats. That's the average. That's the mean. And that gets subtracted from each of these data points. And that's what's happening here. I could look at 31. 31 minus 50. 50 is the mean again. And 31 is right here. It's the last data point right there. Now, we take all of these differences here and these differences, and we take the average again, where we take 27, here's 27, take all those data points, add them all up. Again, this from here. And then that sum is 156, and take the 156 divided by 12 because there's 12 data points. You know, there's 12 numbers here, all through here. And that is 13. So that's how we get the mean. The mean is 50, and the mad is 13. There was 50. That was the original average. And the mean absolute deviation is 13. Okay. What's the difference between... What is the difference between the average monthly temperature for city 1 and the corresponding temperature for city 2? And the answer for that is 15. This is how we get that. So the right here, as we have 23, let me make this a little bit smaller so I can show you there. So here we have corresponding. That word corresponding, I'm going to highlight it right here. Corresponding means this must be January. So we have 23 minus 8. There it is, 23 minus 8. That's 15. And then we have 38 minus 23. 38 minus 23. Well, 38 minus 23 is the next one, right there, 15. And if you look on the third one, 39 minus 24, there it is right there. They're all 15. If I go down all the way down, 31 minus 16. 31 minus 16 is the last one here, and they're all 15. So the difference between each average monthly temperature, city 1, the corresponding city temperature in city 2 is 15. Done. It's very cut and dry there. So based on your answers to exercises 5 and 6, what do you think the mean of the average monthly temperature is for city 2? And what do you think the mean absolute deviation for the average monthly temperature for city 2 is? Give your answers without actually calculating the mean and the mean absolute deviation. So here you go. So we got to think now. If the distance from all of them is 15, we should be expecting something similar between the two data sets as far as mean absolute deviation. So what do you think the mean absolute deviation for the average monthly temperature of City 2 is? Should be about 35 degrees Fahrenheit. And I'm sorry, what do you think the mean absolute for City 2 is? And give your answer without actually calculating. So the mean for City 2 must be 15 degrees less than the mean. So this is the mean, and that's the mean absolute deviation. So, and the MAD must be the same. So, as we have our 50, so if everything is a 15 degree drop, then that 50 drops down to 35 right there. And the MAD would be the same because everything just dropped 15 degrees. What's the difference in the means as a multiple of mean absolute deviation? So in number 8, I believe I have that right here. So the difference in the means, the two means were 50 and 35. Let me make that a little larger here. So going back to what we had, the two means were 50. So the mean was 50 and 35. Those were the two means. So going back over here, the means were 50 and 35. That difference is 15. Of course it is. And the difference in the 15, the difference in the means divided by the mean absolute deviation, that was the MAD from before. 15 divided by 13 is 1.2. So there you go. There it is. The difference in the means as a multiple of the mean absolute deviation is about 1.2. Number 9. So, I didn't do this. Should have done that. So, Mark took 10 random samples from 10 students from 2 schools. He asked how many minutes they spend per day going to and from school. The tables show the medians and the means of the samples. Compare the travel times using distributions of the medians and means. Okay, so they have the medians here and the means for school A and the medians for school B and the means for school B. This is how we can do it. What's going to happen is I'm going to present this as a box plot. And my box plot is right here. So if right here, let me make this a little bit smaller and show you that the, you know what? I think I could do this. Nope, I can't. Never mind. So the medians here, if we made a box plot of all this data, so we could see the biggest number is 40, so 40 right there, and the smallest number is 9, and I could probably find 9. 40? 14? No way. That's like 9 or 10. Oh, 10 right there. So this is a box plot of this information here, and the mean, this right here, is represented by this box plot. So we can see the distributions there. We see these distributions. So we can see, so that's the power of the box plot. If I have this here, all this data, so the medians, here's the box plot for that. And these means right here, here's the box plot for that. So we can see how the data is much more crunched in here. And these distributions look reasonably the same, although this is higher than this. And so, using this, my response is both distributions, move this out. So both distributions show longer travel times for school A, and the distribution of the medians show less overlap. So it's less. So it is more convincing. So they show longer overall. A is longer than B, and we can see that visually. This here, 75% of the data here is at or above the median, and this same thing. The 75% of this data is at or above the median. So longer times for school A, and the distribution of the median shows less overlap, so it's more convincing. Yeah, so there is less overlap. Exactly. They're not on top of each other. All right, let's move on to number 10. And number 10 is on the, next page. So number 10, we have statistical measures are shown for the ages of middle school and high school teachers in 2 states. So we have state A and state B. We have the mean is 38. The mean of high school teachers is 48. The mean absolute deviation for both is 6. Okay, so they did a lot of number crunching for us here. And then they have similar data. The mean of the middle school teachers, high school teachers, and standard deviation. Okay, in which state is specific? In which state is the difference in ages between the members of the 2 groups more significant, and support your answer? Well, my response is this. In state A, you look only at the differences in the mean average ages, but state B, you will consider the variability as well. And I believe I have some more information here. See, if we look at the state A and we look at the difference in the means, right? The difference in the means here is 10. And divided by the mean absolute deviation is 6. We got the difference in the means as a multiple of the mean absolute deviations is 1.7, and then in comparison for for state B, it's 2. So comparing those two here, we can further say the same kind of answer shows up where the difference in the ages is more significant in A. Okay, so 10 compared to 8. Okay, that's what that's talking about. If you look at the difference in the mean ages, but the difference in the mean ages is more significant in B if you consider the variability. So that variability is what that is, the 2 versus the 1.7. Okay. With the next question, we have the tables show the heights in inches for the adult grandchildren of 2 sets of grandparents, the Smiths and the Thompsons. What is the difference in the medians as multiple of the ranges? I have some information for that. And here. So the here is the data. And the range, it goes from 70 to 64 right here. So the range is 6. Our median, if we go from smallest, you have to rearrange this, right? From smallest number to biggest number, which it's not. And if you pick the middle number, the median, that's 66.5. And for the Thompsons, our range is 6 and the median is 77. Now, if I take the difference in those medians right here, that difference in the medians is 10.5, and divided by, so that median divided by our ranges, right? Our ranges are 6, is 1.75. So what this means is the difference in the medians is 1.7 times the ranges, and that is what I have here. And number 12, Jill took many samples of 10 tosses of standard number cube. And when we're talking about a number cube, we're talking about that number die, right? I believe it's called, I believe it's spelled DIE, where it's that, I meant to have a number cube, and it is 1, and then 1, 2, and then 1, 2, 3, and so on. See, roll this a bunch of times, and so this is what happened with her data. Uh, so what would she expect? What might what might she reasonably expect the median of the medians of the samples to be? So the median of the median. So basically, what would you expect here if we have uh, the number die? What are the sides on a number die? It's 1, 2, 3, 4, 5, 6, right? So 10 tosses. What would you expect? I mean, it might. Oh, I could make a dot plot out of this, right? It might happen. Well, everything has an equal chance of getting chosen. So out of 10 tosses, 1, 2, 3, 4, 5, 6, 7, 8, 9, something like this, maybe. But what would you expect? All the outcomes are equally likely. And so if I did this, you basically would expect the median to happen right there. What would happen right in the middle? Well, in the middle is 3.5, right? It's in between 3 and 4. So that's what you would expect here because, like I said, everything's equally likely. So that's why the publisher said here is about 3.5. It should be close to the median of the population, which should be about 3.5. So Ellie and Ramon are both conducting surveys to compare the average numbers of hours per month that men and women spend shopping. Ellie plans to take many samples of size 10 from both populations and compare the distributions of both the medians and the means. Ramon will do the same but use a sample size of 100, whose results will probably produce more reliable inferences. Ooh, I'm thinking this one. And Ramon's sample size is larger and less variability. And there should be less variability in the distributions of the medians and the means. Yeah, the more you get, the more reliable your sample will be. Okay, so Seth believes that it's always possible to compare two populations of numerical values by finding the difference in the means of the populations as a multiple of the mean absolute deviations. Describe a situation that explains why Seth is incorrect. Well, the official answer is this: any situation in which the MADs of the population are not very similar. And what this has to do with is ultimately the word variability. And variability means how far spread out is your data. Now, if we go back to this problem here, here. Now, the two populations had different variability here. And so I think it's, you have to take that into account when you're comparing two populations. If one has a variability, let's say this had a variability of 12 and this had a variability of 1.7, that means that this data is far more spread out than this one. And maybe you shouldn't be comparing them at that point. I can return to our other problem. Oh, we had another problem where, yeah, it was on the other page, where we had two box plots. And one box plot was, like that. And another one was a little bit lower, something like that. And it does seem like you can compare these two. They seem very comparable. But if the other box plot is, let's see, I'm looking for my eraser here. If the other one, if you're trying to compare the two, and one of them is like this, it's kind of hard to touch. So the mean absolute deviation of this one is going to be a lot bigger than this one. Mean absolute deviation is talking about how far spread out is your data. So it's hard to compare these two. And that's what this is talking about down here. That's what this answer in the end is mentioning. So I hope that is more clear for you. That's all you got to know for this lesson. Thanks for watching. Bye.